Hello. Last time we connected the uh, L298 driver, motor driver. We did not use the enable, but we have connected only the power supplies and the motors, and we controlled it in forward and reverse directions. Now in this case, we will control the speed of the motor by using the enable terminal here. This to be supplied by a pulse width modulation signal so that we can vary the motor speed. So we have here the same circuit, just as the same as last time, but we have connected the enable terminal to here. We have here a PWM generator using the LM555 timer IC, and have connected this to the CRO, the oscilloscope, and we can vary the uh, pulse width here through this potentiometer, and we have both signal diodes here, and the supply here is 9 volts. Okay, so this is our circuit here, and we can vary further the frequency by changing this capacitor. But for this setup, we will see how much is the frequency of this circuit, and we will use this output here from Q, output of the 555 timer, and it is being supplied to the enable terminal of the motor driver. Here we have also changed the motor connected to the output of the driver. So this motor now has a speed reading. So this motor has a 1000 RPM maximum. Okay, and we will see whether the speed varies upon changing of the PWM signal that is being fed to the enable terminal of the motor driver. So first thing, we have to check the frequency of this, and we will view the waveform through the oscilloscope, and then we will vary the potentiometer, and we will plot the speed versus the duty cycle of the waveform. Speed of the motor versus the duty cycle of the waveform. So we will try first to check how much is the frequency and how can we measure duty cycle. So now this is our circuit, and I will turn it on. And the oscilloscope is being connected there. Okay, so this is our waveform. Okay, at this setting, the minimum setting of the potentiometer. So how can we measure the frequency of this, the whole period of the waveform? So I will press first the pause here. Okay, I will press the pause. Okay, and I will measure how much is the period. Okay, so the period here in milliseconds. So we can see there, if we will situate our cursor here, that is 270. Okay, 270 milliseconds. So the frequency will be the inverse of that. So that would be 1 divided by 270 milliseconds. Okay, so the frequency would be 3.7. Okay, 3.7 hertz. 3.7 hertz. So in order that I can remember the frequency, I will plot this first here. The period is, I will put here 270. Okay, 270 milliseconds. Okay, so here we have our Excel file, and we have to put all our data here about reading and also the speed of the motor, and we have to plot the curve here. Okay, so the period I put there 270. Okay, and we will go back here to our circuit. Okay, so if I will resume the simulation, we have 270 milliseconds there, and I will vary. So at this moment, at 270 milliseconds, and this pulse here, we have the speed there of about 300 RPM. Okay, so let's see if the frequency changes when I change the pulse width. Okay, so here we will see, I will click the value here, and you can see the pulse is getting enlarged. Okay, the pulse is getting enlarged, but you can see the frequency doesn't change because the period doesn't change. It's still 270 milliseconds until its maximum value. We'll see. Okay, so as I am varying the pulse width, the frequency is still constant, and therefore also the amplitude doesn't change. Okay, the amplitude doesn't change, and the amplitude of that is 5 volts as measured here by the voltmeter. This is 5 volts. See, the 5 volts here is connected to our output at Q. Okay, so the amplitude of the waveform doesn't change, and also the voltage across the motor doesn't change. That is approximately 12 volts here, as we have studied before. Okay, so here the power also, but the power is increasing here because it depends how long did you turn on your circuit. Okay, how long did you give voltage to the motor? Okay, so you can see here, this is our, I will click the pause again. Okay, so here, this is the whole period, and this is the on time, this is the time on, this is the time off. Okay, so this is the time on and the time off. So if you will vary this one, if you vary the potentiometer, you can see, if I will go back to the minimum value, okay, this is the value only, or the time only that you have turned on your circuit, or you have turned on the motor, and this time only you have given power to the motor. So if you will increase the pulse, that means at this much time you are giving power to the motor. So if you will see, obviously the power also changes as long as you are turning it on at this duration. Okay, so if you will put it on a 100%, that means at this period, all of the time, your motor is turned on. So therefore, power is increased at 100% during this time. Okay, so the time on, okay, so the time on divided by the whole period is time on, plus the time off. So the duty cycle is the time on divided by the whole period that is your duty cycle in percent. So that means you have turned on, say for example, if the duty cycle is 50%, that means at 50% of the time you have turned on your motor. Okay, so I hope that is clear. So we will now go back to the minimum value and we will see if the motor speed is increasing, and then we will plot there on our table. Okay, so I will start the simulation. Okay, so that is the minimum speed. Of course, if the duty cycle is 0, okay, we can put here in the Excel file 0, and that is the minimum position, or the minimum position of the potentiometer. So how much is our time here at this duration? So this is, okay, this is 42.50. Okay, so this is 42, or let us say 45. Okay, so this is 45 milliseconds, and then the motor speed is 260 rpm. Okay, the motor speed is 260 rpm. Okay, sorry, motor speed is 260 rpm. We will move this here so that it should be visible. Okay, 260 rpm, that should be multiplied to 1000. Okay, so I will put it here, 260 rpm. No. 260 rpm, yes, 260 rpm. We'll put it here. Okay, this is 260, and the time is, I will say here, 40. Sorry, that is 45 milliseconds. So I will put here 45 milliseconds on the reading one. Okay, okay, so the second one, I will resume this. I will resume. Okay, now I will adjust this one. Okay, so how much is the second time, second reading? That is 67. Okay, 67.5 milliseconds. Okay, so 67.5 milliseconds, and the speed is 380. So here, this is the speed is 380. Okay, and the time is 67.5. Okay, 67.5 milliseconds. Okay, then next one, I will clear the cursor so that it will be clear. Okay, so next one, this I will increase it here, and the time is, we'll click the pause, and the time is approximately 90. Okay, so it's 90 milliseconds. So we'll put here 90, and the speed is 500. Okay, 500 RPM. Okay, this one, 500 RPM. Okay, and then I will resume, clear the cursor. Now the next reading is, how much is the time? How much time here? That is 110 milliseconds. So it's 110. I will put it here. 110 milliseconds. Okay, 110, and the speed here is 550. Okay, 550. Okay, and for the fifth reading, okay, I will increase this one, and I will clear the cursor. Okay, I will click the pause, and how much time now? That is 132.5. Okay, 132.5 milliseconds. Okay, and the speed is 640. Okay, the speed is 640. Okay, so we will proceed to the sixth reading. Okay, I will turn this on. Okay, and I will increase this further. Okay, I will click the pause. I will clear the cursor. So how much the time here? 155. Okay, so the sixth reading is 155 milliseconds, and the speed is 690. So the speed is 690 RPM. Okay, and I will go to the seventh reading. Okay, I will increase. Okay, I will clear the cursor, click pause, and how much is time? 177.5. Okay, so seventh reading is 177.5, and the speed is 760. Speed is 760. Okay, speed is 760, and we can see here this window, this cell, this is the duty cycle. Okay, it is now 65.74%. Okay, so next reading, the eighth reading. Okay, so I will resume eighth reading. Okay, so I will pause first. Okay, we'll clear the cursor. Okay, how much time now? It's 197.5. Okay, so that is 197.5. That's the eighth reading, 197.5, and then the speed is about 830. Okay, 830 RPM. Now the ninth reading. Okay, the ninth one. Okay, click pause. Okay, we'll clear cursor. That is 220. Okay, 220 milliseconds. 220. Okay, and the speed is 900. speed is 900. Okay. Now, the 10th reading, we will click again resume. Okay, 10th reading. Okay, how much the time? That is 240 milliseconds, and the speed is 930. Speed is 930 RPM. And for the last one, okay, so this is the full now, and this is 240 milliseconds. No, that is, sorry. So that means that is the full 270. This is the old reading, so I will delete it. So this is now the full 270 milliseconds. Okay, 270. So I will put here 270. So that would be 100%, and the speed is 980. So the maximum speed of the motor, as I have said before, is 1000. So at this moment, it cannot reach the speed. Depends upon the circuit limitations that we are having. Okay, but on this experiment, at 100%, the speed is 980, and we have plotted, okay, the characteristics of speed versus the duty cycle. So you can see the lesser the time that you have turned on your circuit or you gave power to the motor, see, it's the least speed. Okay, so as you are giving time of turning on, the speed also increases. Okay, so remember that the duty cycle is T on divided by the period that is in percent. So 16.67 until 100%. Okay, so if you will see the circuit again, I will turn this off so that the CRO will be removed. So this is our circuit. I will maximize this. Okay, so we have same circuit as before, but here in order to control the speed, we have to use the enable terminal. So here we should supply a PWM signal. Okay, PWM signal. So the PWM signal is accomplished by the LM555 IC, and it is suitable to control the speed of the motor. And of course, we can use microcontroller in order to supply the PWM. Okay, so but here we want to use a source which is different from microcontroller, and we can see it's still working as long as you have the PWM signal fed to the enable A. So in the same case, if you will use the second motor connected here, okay, we use only one motor, but we can use also two motors at the same time. So it depends upon the design of your circuit. Thank you.